Welcome to our lecture on compiler construction. Today we are going to discuss another static analysis method, so data flow analysis that's concerned with reaching definitions. So reaching definitions, in contrast to liveness analysis we've seen before, is now a forward analysis, so we're going in the direction of control flow in our control flow graph, whereas previously we were going against the direction of control flow. And reaching definitions is pretty similar to liveness analysis. We'll see this in a moment. And it can be used for similar things like finding uninitialized variables in code, even when we consider different paths through which the execution is going. And we can use this for an optimization copy propagation. So reaching definitions analysis, of course, as the name says, is concerned with definitions of variables. So as we've already seen, a definition of a variable x is a statement which assigns a value to a variable x, like that one over here. And we've already seen in our previous examples that each assignment is prefixed with a unique label, like D1 and D2 here. So that makes it easier for us to identify each single assignment in our program. And what's important is, of course, if we have several assignments to a variable here, different occurrences of the same assignment become different definitions. So if we have an assignment x equals y in two different parts of our code, they are different assignments here for our analysis. And for our reaching definition, we now have to define what reaching means. So a definition of a variable d reaches a program point p if we can find a path from the point immediately following our definition of a variable d to this program point p, so that the variable d, the definition of that variable, is not killed along that path. So for example, on the right hand side we have d1 y equals 3 and we have d2 x equals y, and if we only have these two instructions here, then d1 is a reaching definition for d2, so the value of y we initialize in d1 is the one we can read and we use in d2. In the example below here, we have another instruction in between. So we have the first instruction y equals 3, the second instruction y equals 4, and the third instruction x equals y. So d1 here is no longer a reaching definition for d3 because we have another instruction, another assignment in between, which assigns a new value to y. So here we see that the definition of a variable is killed between 2 points when there's another definition of that variable along the path. So, for example, a definition or an assignment r1 equals r2 plus r3, of course, kills any previous definition of r1 that came earlier in the path. So, reaching definitions is different from the variable uses or the computation of expressions. So, labels are not associated with reaching definitions, and for this case, lexically, some computations are not treated as different entities for the analysis. So for liveness analysis, we are analyzing variables here, or in case of code generation, we would be analyzing virtual registers, and liveness doesn't actually care about specific uses of a variable here. Reaching definitions, on the other hand, analyzes operations on variables. So we've seen each def is treated differently. So we have forward data flow analysis now in our reaching definitions analysis. And so we analyze values as the propagation occurs from the defs downward. In contrast, liveness was a backward analysis. So we went backward through our control flow graph. So for this, we need to define a set of data flow equations as before. So we say that a definition di from our defined variables here that defines a variable x from a set of variables reaches a certain program point u if this definition di occurs on some path from our start of our program to our point u, and this definition is not followed by any other definition of the variable x on this path. So we can write data flow equations for this case. So essentially we have in n, the information is either just our initial information if our block n is a start block. So bi might represent information coming into our block, or might simply be an empty set if we just start our program here. And if our block n is not a start block, it's the join of all the preceding blocks for their outputs. So we're looking at a certain block n, and we're looking at that block's predecessors we call p, and we're looking at all the outputs of all the predecessors of this block. We're joining them together to obtain the input set for our current basic block n. And on the other hand, our output set is defined by the input set we've just determined, and then we subtract the killed variables in that block and join them with the generated variables in our block here. So here you see the use of the join operator to capture this anyPath nature of data flow. So we have to consider any paths coming into a basic block in order to figure out what data is actually relevant for this block here. So this is of course similar to liveness analysis, but now the data flow is forward, so we're going from top to bottom in our control flow graph instead of the other way around. So to perform a working reaching definitions analysis, we have to make some assumptions here. So for each local variable x in a piece of code, we assume that some fictitious definition x equals undef reaches our entry. So we have a state we can actually start from. So this is actually not required in every case, but we need it for optimization of copy propagation, as we'll see later. Now if we figure out that the definition x equals undef reaches a use of x, then we know we have a potential use of that variable before it has ever been defined. So if there's some path where we can actually figure out, oh, x is still undef when we try to use it, there might be a problem and we can do something about it, like throw an error message or try to fix it somehow. So whether this happens at runtime depends on the actual results of the conditions along the path, so which branches we take, which loops we are actually going to execute one or more times to reach the given program point. So when we look at the gen and kill sets, gen contains the downward exposed definitions in a basic block n, whereas kill contains all definitions of all variables that we have modified in n. So for reaching definitions analysis, gen n is always a subset of kill n. Let's look at an example here. So we have our example program that you probably know from last time around. So here we see we have a number of instructions, and each assignment here is actually prefixed by a unique identifier, by a unique label like B1, A1, and D1 here. So labels of assignments consist of variable names and instance numbers. So B1 is the first assignment to variable B, and so on. So we have certain definitions, and now we said we wanted to add information to our analysis that tells us before the first assignment all variables are undefined. So before block 1 we can add virtual definitions A0, B0, and so on that represent the special definition of that variable being undefined. And since we have a join operator here, a confluence operator that is a join operator, the initial value at each program point is actually the empty set, and then we join the information together. So like before, we can do analysis, and we have to do the analysis in separate iterations here. So starting from gen and kill set, we can obtain from our basic blocks, as we've seen last time around. We can now propagate our global information by joining information together here, so we can obtain the in and out sets in our first iteration, and then we can run this iteration again, and we can figure out what has changed in the second iteration. So here we have to consider that definitions reaching the exit of N6, block 6, and the exit of block 7 in iteration 1 have to be propagated to the entry of block 6 and block 3 again, because we are running loops here. So essentially when we are in B6 here, which is N6 here on the left hand side, so we could actually run up here again using this arrow, this path in our control flow graph, or when we're at B7, we could run up here again to B3. So this requires an additional information, and this requires to propagate that information back up to the entry of B5 and B3 respectively in order to ensure that we actually capture all the possible ways we can run through our program. Now, when we consider the data flow through our complete program, we can take this a bit further, so we can actually define chains of defs and uses and the other way around. So reaching definitions, this analysis is actually used for constructing so-called useDef and defUse chains, and these always connect definitions of variables to their uses or the other way around. And these are the basis for facilitating several optimizing transformations here. So for example, in this right-hand side example, we have the defUse chain for our variable a here. So for example, we start here with the first definition a1, and this propagates here to that one here. Here we're using a. Here we're using a again without redefining it in between. The same happens here. We're using a here without any intermediate redefinition. The same happens here. And so we can figure out which passes are actually defUse chains for our variable here. And of course, chains always have to start at a label because they start with a definition of a variable here. For variable c, we can take another look here. So defUse chains for variable c, they have a special problem here. So as we've said, we have introduced, and usually we don't note them here, special labels indicated by an index 0, so like c0 here, which initializes all variables to be undefined. So this c0 would actually say c is undefined. And if we take a look at basic block 1, we see that 2 lines downward from there in a1, the value of c is actually used. So this value can actually propagate somewhere. It can propagate to a1, but it can propagate to other uses. So it could also propagate, for example, from here to here. And then there are other paths, defUse chains, where actually values get propagated. An interesting case is c1, where actually a value of c is propagated again. So we assign something to c. So we could run through this loop here, through that loop here, up here again, and we're reusing the value of c we've just initialized here by using this assignment, because we are not doing any reassignments to c on the path in between. So the biggest problem here is really that a definition of c0 can actually reach some uses of c, like here and here or here. So this in turn means that we can use c undefined here, and for example in b2 this can mean that variable b would be potentially undefined because we cannot really figure out what the value of variable c is. So again, we see this here, and the important thing is that this analysis we're performing here can actually make use of transitive effects. So we can look what happens from going from one basic block to the next and to the next again, and so on. And we can then use this to perform this possibly uninitialized variables analysis. So we can figure out, is there maybe at least one path that reaches a current program point where our variable that is used in this basic block we're considering right now is actually not used at all. So this possibly uninitialized variables analysis is important because, again, it helps us to identify possible security problems in our code. So for definition xi of a variable x, reaching definition analysis discovers a set of definition reaching passes. So essentially this is a sequence of blocks b1 to bk, and these are a prefix of a potential execution path that starts at b1, so that b1 contains the definition xi, like up here. bk is either end or contains another definition of x, and no other block in the path contains a definition of x. So some definition reaching passes for variable c in our example would go using our transitive analysis through here. So we go from b4, where we define c, to b7, where we don't do anything with c at all, and then up the loop to b3, where C is actually redefined here. Another one would be going from B3, going down the right hand side to B5, where C is not used at all, going down here to B6, where C is only used but not redefined, going to B7 and then up again to B3, where it's redefined, and another pass might be going here, B3, B5, B6, and then it takes another iteration through a loop, so we're going through B5 and B6 again, and then finally we're going up here again through B7 up to B3, where we're redefining our variable as C again. So we can use reaching definitions for yet another optimization, and this optimization is called copy propagation. So a definition of the form x equals y, so we're just assigning the value of one variable to another variable, is called a copy because it merely copies the value of variable y to variable x. And when such a definition reaches the use of x, and no other definition of x actually reaches that use, then we have an identity. So we can actually replace the use of x by whatever is y. So essentially, we save ourselves a copy because we know the values of x and y have to be identical at that program point here. And so copy propagation here in our example would make use of the fact that we initialize b to 4 here, so we have a constant here in b1, and this is the only definition which reaches the uses of b in blocks b3, b4, b5, b6, and b7. So essentially we have b equals 4 here, and then we can propagate this here, this b here by a value 4, and again here, and here, and there, and also there. So essentially we save a bit of overhead by employing this copy propagation analysis here. So in this previous example, the right hand side was constant. So with variables on the right hand side, like we've seen x equals y, replacing a use of x by y requires an additional check to ensure that the value of y has not been modified along the path from copy to use. And we can actually define a variant of our reaching definitions analysis to accomplish this. So when we restrict our definitions to copies, so we don't consider all defs but only copies of variables here, a def x equals y is then contained in our gen set if it's downwards exposed in n, so if it's not being followed by a definition of either x or y, and it's contained in the kill set if our block n contains a definition of either x or y. And then we can perform a reaching definitions analysis using these constraints, and we know if one def reaches a use, we can then perform copy propagation here. Otherwise, we cannot be sure, and so we can't use this optimization in that case. So this copy propagation itself doesn't actually improve the program performance, but it has the potential of creating dead code. So when we use copy propagation using the knowledge that we have an assignment x equals y, it's possible that we can replace all uses of our variable x by y, which means everything that uses x would be dead after the assignment. And then the assignment can be safely deleted. So essentially, we're not saving lots of performance, we're saving a bit of code space. So essentially, it's one small optimization, but an important one. And of course, again, this is a very old optimization, as we've seen with the other optimizations before. So the first time I found it being mentioned was in an overview paper, a catalog of optimizing transformations by some IBM researchers already from the year 1971. So this one was a bit of a shorter lecture today. Thanks for listening and see you next time. Bye.